All right. So I guess let's get started.
Okay, sure.
Good afternoon, everyone. Thanks for joining. Welcome to the NUSCS Colloquium. It is our great pleasure to have Professor Munchun Chan for this month's colloquium. Professor Chan was promoted to full professor effective this year, January 1st, 2021. So we are going to hear a broad overview of his research area. And I thought who would be better person to ask for introduction than the head of the department when he joined NUS long ago. So I'm going to ask Professor Sanjay Jain to introduce our speaker today.
Okay, so Manchun joined us about 20 years back in 2003. And at that time, actually, we had a few people from the industry joining us. And we usually don't get that many from Bell Labs, etc. So we were very glad to have Manchun and Cheong both from Bell Labs at that time joining us. So I'm glad that they took it up and joined us and continued with us till now. So I suppose we are not so bad compared to the industry. So we are a good place. And Manchun can say more about it, I suppose. I suppose he's happy here. Okay. So yeah, so he did his PhD from Purdue, from Columbia, his bachelor's from Purdue. And his research interests are in the general networking area. So he has done lots of work, lots of patents in networking. So let's welcome him for his talk on programmability in the switch data plane.
Okay, thanks, Sanjay, and for the intro, and of course, thanks, Kudip, for organizing. Of course, thank all of you for taking the time to attend my talk today. So, okay, I guess I'm Manchun, and let me just give a brief intro of myself. I guess Sanjay already mentioned it. So I got my bachelor's from Purdue, and then I got my PhD from Columbia, and I didn't join academia right away. In fact, academia was actually not in my original plan. It's kind of accidental. I just got into academia, but anyway, I joined the industry for about six plus years. I was in Bell Labs, and I guess Cheong was there with me. Though we are in different location, and somehow two of us decided to make a career change, and he came back first, and I came back after him, right? So Sanjay mentioned 2003. I interviewed in August 2003, and I joined in, I think, official was December 26th, I remember. December 26th, 2003. So John 2004 is about right. Is about right. So back then, in case you're curious, the dean was Joksan, and the first chair was Roland. Roland, remember? You are the first chair back then.
Right.
So I must say, you guys did a good job, right?
I think our track record is quite good actually.
Yeah. I remember.
I mean, not just me, of course. But,
yeah. I mean, we got a lot of people who joined. I was considered the last of a wave. After me, things slowed down. But before me, I still remember people who joined a few years before me was like David Su, Visan, Tulika, Abid. A lot of people joined around that time. They were ahead of me, but when I came, there are a lot of. It's I guess like all you guys, all the assistant prof, similar, right? Some earlier, some later. But a lot of you joined within these 3 or 4 years. So my time was the same thing. A lot of us joined within that 5 to 6 years. I guess now most of us are still here. So I guess you're happy. All right. Okay. So my area, computer networking. I guess I'm kind of rather focused in my research. I mainly work on networking. I do collaborate with other people, other stuff. But I guess on looking back, I kind of try to look back at what I have done since I joined, right? So because when I joined from industry, it's rather difficult to continue some of my work because the industries are different focuses. They have their own test bed and access to different systems which I don't have when I came back. So when I came back, I kind of did the safe thing, which is to work on the popular areas of the era. So things like mobile ad hoc network, delay tolerant network, and vehicular network, right? This is kind of the stuff I work on when I was assistant prof. And then I got my tenure. I said, time to maybe change, look at something different. And I guess, I was riding on the wave of the IoT waves, right? All these low power devices. and all these new sensing modalities that are available on the sensors or on the mobile phones. So kind of roughly, I work on that broad area. So I did work on low power sensor networks. I guess my kind of specific niche was something called synchronous transmission, right? It's something that we actually did quite well. I think our group is kind of fairly well known for this very niche area on how to design multi-hop low power wireless sensor network protocols. And I also work on mobile sensing, which is basically all this new new sensing modality that would become available on commodity devices. And I did a bit of work with Smart. I think Lishan back then was still with Smart. So we have a lot of work together on how you use your mobile phones and sensors to understand the environment and how to do smarter transportation. So more or less, when I applied for promotion, this part forms the bulk of my work. But already I was then starting kind of a third line of work, which is kind of what I'll present today, which is that around 2009, 2 to 3 years ago, data centers have been around, right? But people, it's kind of become bigger and bigger. And people really say that, we need to do something different because they're getting so big, they're getting so messy, and yet they are becoming really more and more important. Most of our data are stored in some kind of a cloud or data center out there. And plus, there was this, of course, this hype of 5G, and then now they want to talk about 6G. So what is the common thing is that, they are looking at how do we relook at the design of how network should be built, and how do we exploit some of the more recent advances in the network hardware technology. How can we use this to design network differently and hopefully in a better way, right? So I'm kind of riding on this new effort on data centers and 5G and 6G. So the overall area, you can call it software-defined networking, and particularly on something called programmable network data plane. Right. Okay. So so this is kind of the blue stuff what I'll talk about today is on this area called programmable network data plane. Okay. So I think to kind of give you guys the background, I need to kind of start from something to give you the historical context, how people think about all this network devices, right? So classic notion of a network device is you have some hardware-based solutions which implement some specific fairly narrow class of network protocols, right? They're fairly rigid. They tend to have to obey the standards. So they are proprietary, and then they just do a small number of things very, very well. And this is kind of in line and okay with how people think about how the internet should be built, right? So the internet is supposed to have this minimumness mindset. You put all the complexity on the edge. They want end-to-end, it's called end-to-end argument. The network should be very dumb, do the minimum stuff, and everything else that you want, all the complexity, all the fancy applications, put it only on the endpoint. So in some sense, the developing applications over the internet is really what the design is catered for, which is great for most people. But for people who are doing networking research, then now we have a problem because there's very little you can do in the core of the network, because all they care about is one basic function, which is just do packet forwarding, right? And I guess as the network becomes bigger and people say no, can I do more? It's become clear that it's just very hard to manage because there are very little information they can extract out from the network. And also it evolves very slowly. Changing any of these protocols, because they are always built into the hardware, takes a lot of time. And also very, very difficult for the network researchers to innovate. Because just imagine changing TCP, or any of the routing protocols in the internet. Not that that there are no better ways, but making an impact is very hard because the internet is just amazingly difficult to even suggest small changes. The changes are all supposed to happen on the edge, right? So the legacy era, okay, is that basically you have a so-called a fixed pipeline. This is how the switch looks like. You have this, it's so-called a parcel that looks at the headers, extract out the appropriate information, and then you have so-called multi-stages. You just match the header, and then you perform an action. The action could be, you change the header, you send it to a particular output port, or you drop the packets, or you do rate limiting, right? So, or you do firewall stuff, right? And you go through, pass this out. So usually you will buy a router or switch. These are all given to you. It's all closed. You're not supposed to touch any of them. And on top of it, what you do is that you can configure the switch or the routers. So for example, the common thing is some kind of a so-called CLI, which stands for command line interface. So you just, basically, I did 203 this semester, right? As my teaching, configure the router is still very painful, right? I can tell you that, it's not easy. So, but this is how the legacy system works. You have a very restricted set of functions you can program, and you can't really change them, right? So, but we all know this problem exists. So for a very long time, at least the research community say that, we really have to do better, right? We should make the control more open, make it more extensible, make it more programmable. It's kind of a goal and a vision, a wish list, right? And of course, we take this, this analogy with the PC world. You can take Linux, which is open. Okay, back then it will be Unix, and then you can run it on any hardware, right? This is how we should get all these network equipments. You can buy a generic white box switch from any vendor, and you can run your own operating system, and it should work, right? It should be known from, and everything should be controlled by this open programmable network interfaces, right? And people tried, but I guess the two factors: the market is not ready because you have very dominant vendors like Cisco and Juniper of that era. Plus, I think also the technology wasn't ready yet. People do not know. People want it to be open, but we do not really know what does it mean to be open, right? How do you really describe what is needed in the hardware, and how do you actually build a switch that can do that? I think back then we really do not have the capability yet. But many people try. So I think people like the IEEE standards. There's one called programmable network interfaces, in 1998. And the IETF world have this general switch meshing protocol, right? So they are around. In fact, there are many more proposals beyond this, but none of them took off, unfortunately. Right now, took off, it all become fairly highly academic. So the first, I would say, successful kind of effort in this area is something called OpenFlow, right? So this is your beginning of your SDN era. SDN, software-defined networking, right? So OpenFlow was actually pushed by, the group from Stanford, Nick McEwen. I think the story that we heard was that, Nick could build hardware. So he can actually build the hardware, and he can actually kind of manage to convince Stanford to actually deploy these kind of switches on campus. So he can build it, he can build the whole ecosystem, and he can make, at least have a trial on the campus first. And I guess it got really popular over the next roughly 10 years. So the underlying hardware is still same, right? You have a parcel, you have so-called the mass action pipeline, right? So pipeline means that as the packet comes in, right? Every clock cycle, the packet moves to the next stage. So in this case, I have a 4-stage pipeline. That means a packet will have to work for 4 clock cycles and then get out, right? So anytime, up to 4 packets can be in the pipeline, right? So the packet takes actually 4 clock cycles to be completed, but every clock cycle, 1 new packet can come in, right? So it's a pipeline. So, but what the earlier SDN does is that it still defines an open interface on this level. They call it OpenFlow. I think you still can buy switches right now that so-called support the different OpenFlow versions, 1.1 all the way to I think 1.8 or 1.9 or something. We even have some of this in the lab. In fact, it's getting fairly standard now, right? But it is kind of the first successful SDN deployment, and people are very excited. But after about 10 years, kind of the excitement has gone down because they realized that there's only so much you can do because the network core did not change. You still have a fixed set of APIs, and you program using those APIs, OpenFlow, and they're defined by the standard, right? How what you match and kind of what are the actions that you perform, right? So this is not really there yet, right? So the logical goal is that you really want to change the behavior of how the packet processing is being done, right? Because now it's how do you do it, right? So I'm sure this will evolve over time. People want more and more powerful expressive capability. What we have now is something called pizza. Not just that we can eat, but it's a protocol independent switch architecture, right? Pizza. And basically the model kind of describes roughly how the switch looks like. And then you have a language called P4 that helps you to define the exact behavior that you want to be performed. So it means now the hardware, all right, the parcel you can program. And why this is good? Because now you when you buy a network card, it doesn't you don't worry whether the card will support your network protocols or not, because the protocols that you want to support and how the headers are interpreted can now be programmed in runtime. And how the packet is being processed in terms of how you do the matching and the actions, all programmable, right? So now if your pizza and your P4, and now you can actually define a kind of abstract behavior of what happens, how processing is done on the switch. And on top of it, of course, you always need a set of control. You run some high-level control process on top of it. So previously, this is open, right? You could use OpenFlow or called the command line interface. So what is, I think, very interesting now is that the interface now is actually defined by what you do here. When you write the program, you define how your operations, how your switch works. From this program, you can actually have a runtime that will now auto-generate the set of APIs that you export. So now it's much more flexible, right? I'm sure people can make this even more programmable, which is kind of gradually happening now. But this is, to me, a kind of the big change. I can make this lower part programmable, and APIs are actually generated by the programs that I write, right? So this is kind of the hardware that we are all using now. There are the actual switches you can buy. The one of the popular one is called Tofino. It has been brought up by Intel. So now all these are under Intel. So we have a Tofino 1 in the lab. We are buying a Tofino 2, and Tofino 3 is supposed to be coming. So, right, so kind of roughly, now it's programmable, right? So what can you do? In some level, is what you can do is limited by, of course, what is available, and also limited by what you want to do and your so-called your creativity. A lot of papers is also about I can do a lot of interesting work, okay, but the underlying functionality is that basically now you can store states. Previously, it's very hard to store states. Your states are basically the lookup table, your routing entries, maybe some counters. But right now, the states is whatever you want to store. You write a program, you have internal states, and you decide what you want to store, right? And you can do simple computation, add, subtract, and simple stuff like this. Okay, another thing is that now you have very, very detailed information about what's happening in the switch. Because your program runs in the switch, right? We call it the data plane. So the packet processing is called the data plane. The controller, if we call it the control plane, right? So now you can get fantastic, detailed information about the switch, how many packets are queuing, how long you stay in the switch, where are they going. Previously, getting this information, you had to get it from the control plane, which is very slow. Think of it, the control plane operations on the orders of milliseconds or faster, right? Because you're doing a query on the registers. Whereas if you do it on the data plane, the packet processing rate is basically roughly 1 billion packet per second. It means your time resolution is on the orders of nanoseconds. So it's between nanoseconds resolution and some milliseconds. So at least about 1,000 times or more finer grade, right?
So yeah? Sorry, just a quick clarification.
Sure.
Can you go to the previous slide?
This one, right?
Yeah. So for the bottom, maybe this is a clarification because I don't know this stuff very well.
No. Yeah.
So since the bottom part, so this is the bottom part is programmable.
Yeah.
So what is the meaning of storing additional state if the decision that is being made here, which I assume is the routing, right? The decision that is being made here, if that is not stateful, what purpose would be served by? I understand that this is programmable and stateful programs can be stored here.
Yes.
But as far as the activity that I see, the decisions being made are not necessarily stateful reasoning. So you would not be routing packets elsewhere based on the previous session or something. So maybe this is something, because of my lack of knowledge in this area, you can hopefully clarify.
No, yeah. So, thanks for the question. So I guess one of the more obvious thing that you can do is that you can do very fine-grained monitoring. So you can keep counts of the flows. You can keep track of what happened. So I think in my talk later, I will give the examples about how you can do so-called fine-grained monitoring. And what others have done is that, because for example, you can do caching, you can do very fast lookup. So basically, think of it, I store I have a very high-speed directory system inside the data plane. So if you want to do a lookup for certain information, you store the key in the data plane. So now you can, instead of having a packet hits the end host and do the query, I say, where can I find this piece of information? You actually do the lookup in the switch itself.
I understand that. That is doing the same decision, the stateless decision more efficiently by caching from previous sessions. But it's not that different, more stateful decision is being made because you stored some state from previous sessions. That is not the case. That is, you route the packet somewhere else because in previous sessions, some decision was made. That's when we call it a really stateful system or a stateful software. Here I understand that there is some state in the system and the same, it's still stateless, but the same decision can be made more efficiently.
I guess it's like, are there some more complex logic reasoning in the switch? I guess right now, probably we're not there yet, because what you can do on the switch is not that, we can't do a lot on the switch. So when we say state, it's just, it means that, for example, they do it for load balancing. They remember previous decision. I have done this, so maybe I can send this.
Okay.
Like stateful load balancing.
Okay, great. Yeah. Okay, thanks very much. Yeah, thanks.
Yeah, no problem. Okay, so
just along that question, right?
Could you imagine, for example, that you just do a DNS query in the switch?
Yes, possible. Yes, it's possible. In fact, definitely, this is clearly one of the possible. The thing is this, right? So you can only store so much data on the data plane. So now is that you have to be smart about what you want to do in the switch. You can't just dump everything into the data plane. So the best is like a lot of this, like so-called the 80-20 rule, right? Those that happens very, very often, you can put it on the data plane. So they will serve 80% or 90% of the traffic. Then the other 10% that you miss, you just perform them normally. So just this recent paper called, I think, Sailfish, that's what they do. They basically say that, if I know these guys are coming, I can put their state in the data plane so I can handle them faster. Those that are more complex, which the rest of the 10-20%, I'll just do it normally. So it's kind of work as like an accelerator. There's also, I think, people have tried, not perfect yet, but they're actually trying to offload some of this a very simple operation in the some of this machine learning operations, very, very simple ones, extract it out and put it in the switch. That they can kind of use it as a accelerator for some of this ML operation, right? So basically, is how be smart about what you want to put on the switch. Choose something that basically that is relatively simple, needed by everybody, and don't require a lot of a memory, but it's done repeatedly, because the benefit of running it here is very fast and almost no extra overhead, because your packet has to go from A to B anyway. So if I can process on my way there, then I basically almost do not add any additional latency. This is kind of the thing. So I guess people also I think like Jalin talked about, he has done some work about running some kind of a consistency protocol in the network. That also we have tried. Basically, you implement some of this like a Paxo-like protocol in the data plane, because that's a strength. Is that the packet just go through the switch because it has to travel, and along the way it gets some of the work done. Okay, not all the work, but some of the work done. Okay, can I go on? All right, so I guess now is what you probably cannot do. So you have to be smart about what you want to put in the data plane. It's not going to be a generic, computation platform. So as mentioned, right, it runs at the pipeline. So you cannot store the pipeline. That means whatever code you write, it has to be done within a clock cycle and then move to the next stage. So you write your program to download basically, operation into different stages, and in each stage, it has to be completed within that clock cycle. So imagine if I do a 1 billion packet per second, with every nanoseconds, the packet has to move on to the next stage. The whole operations might be so-called performed over roughly say 10 to 12 stages, but the way you compile it right into the code, you have to move on. You cannot store. So that's where sometimes the so-called the learning curve to write the code can be quite high, because the model is just a bit strange for a lot of us. That you cannot just write normal C code. Your code has to be kind of amendable to be run in a pipeline mode. Okay, so of course, no, you can't run a loop here because you cannot stop the pipeline, but you can loop back your packet, right? So if you think your packet needs more processing, you can actually loop it back, which we have done it quite often, right? So you cannot run a loop to slow down the processing on the single stage, but you can loop back your packet, right? So at least in the earlier version, there's no complex processing like floating point. But they are coming up with a new one. Tofino 2 is still just faster. I think Tofino 3, they are talking about adding more computation capability that is make it more amendable to support some kind of computation that can be used by some of the higher level applications, like some kind of AI ML kind of applications. They're looking at it. So I think it's coming. All right, and finally, okay, this is the hardware constraint. People who design these things apparently, will spot it very quickly. Your memory, has only, can only be accessed once per stage. So that means that you can update the thing once, right? So this has some fairly big impact on how your program can be written, right? So all these are the constraints. You cannot run anything you want. There's only certain things you can do. Okay, so I kind of give it the background. I guess I should speed up. So when I prepared this, I have in mind, it's like, do I want to talk about one piece of work and give you all the not all, some of the details, or I try to kind of touch on different topics. So I decided that maybe I should just be short, because I kind of want to share these things that kind of let you guys see how one can do different kind of work on a platform like this. So I kind of look at 3 different pieces of work. One is how to build a network debugger. This is published this year. One is about how you design a data structure that fit more into this kind of a pipeline architecture, published last year. And one is on, with this, we can actually think about so-called designing or what's the design supporting 5G in a different way that is not kind of possible before this, right? So this is actually going to appear in Mobicom this year. The conference has been postponed to next year Jan. So I hope no more whatever. So accepted but not presented. Okay, I'll do the first one first, right? So as I say, I try to give you a big picture, an overview. I'm skipping some of the details. I just want to share with you kind of how some of the high level interesting things that can be done and not about that. So okay, so the motivation here is that data centers, is the workhorse of the internet. A lot of our data processing are done on the internet. Okay, and they become really, really large. There's a lot of problems in terms of challenges in terms of running them and maintaining them, right? So there are a lot of problems. So this will be concrete. We're only looking at one class of the problem, right? Which is so-called transient bugs, right? Or transient faults. And one of the most kind of a well-known form of transient problems is they're called microbursts, right? So why is it called microburst? It's because if you run the network, suddenly you will have this intermittent congestion event. It means the queue gets full, and then you get either very long delay, or you start to have like a burst of packet drops. And they're called microbursts because they actually last for only 10 to 100 microseconds, right? So it's very short, and they can happen at any time. You cannot predict when they will happen, right? So there are a lot of reasons why it can happen. Basically, it's a short-term congestion. So two that probably easy to understand is basically you have a TCP incast. For example, you do this scattered and gathered application, right? You have these guys, create a lot of jobs, send to all the workers, right? And then it gets the data back. When it gets the data back, actually, if they all finish about the same time, you can get an incast. Everybody is trying to send the data back to the same guy, right? So, and this is happen over a very short time of like tens of microseconds. So suddenly you have packet drop when you are done trying to collect data, right? Or you have traffic that are bursty, for example, UDP traffic. So these bugs are actually very hard to find, because they are very transient, and you actually do not know why. They have no clue why it happens. So when it happens, you have suddenly long latency, suddenly you lose packets. And for data centers, they really want to keep so-called their QoS, quality of service, high. They try to avoid dropping all this packets. So they try to identify them. And because they are so short, standard monitoring tool, you cannot even find them, because if you average over like a few milliseconds, on the average they don't exist. The average is that everything is fine. But if you look at very short term of like hundreds of microseconds, you have packet loss. So now it means that you really need a better tool, and such problems are known to be quite common, right, in most of the data center, because also the traffic type, the applications that you have, also the links get much faster, and they are very big, right? The so-called fan-in can be very large, like hundreds of thousands of guys sending some data back to a single guy, right? So things can happen. And see, the traditional techniques based on averaging, because usually the way we do it now is that we actually monitor all the ports and routers. Every port, the statistics, let's say every hundreds of milliseconds or every few seconds. And if you do it this way, you don't even see any problem. You only know that packet loss, but you have no even idea, that such things has happened, right? Of course, there are also more specialized commercial solution. So they will tell you that a microburst has occurred, but they don't tell you why it occurred, right? It's okay, on this link, we have 2 or 3 microbursts, you drop 200 packets, but you have no clue why it happens, right? So to find things like this, right, the so-called transient fault, what do you need from the network, right? First, you need the visibility. That means all of this averaging, sampling technique probably will not work well. You need actually kind of per packet visibility. And this packet now, remember, is billion packet per second. And you also need to basically know the history, because when something happened, like a car accident happened, you want to know what happened before the car accident, right? Like who drove into someone's lane, who stepped on the brakes. So same thing here. In order to do the debugging, you need to know the history. You cannot start collecting only on the trigger of the event, right? This is your we call it a retrospection. And finally, you also need to correlate, because to do debugging at this level, you actually need to correlate the information for multiple switches, right? So you need to correlate them, right? So there are, of course, this is a big problem. People have a lot of solutions, especially when you have such a programmable network. The obvious thing is that, well, I just have everybody send a postcard, right, to the controller. This is kind of a more brute force solution. Of course, you can reduce it by doing a trigger, but still, you're collecting a lot of information, right? Clearly, you will not be able to do monitoring continuously, right? So you will probably have to, so-called do it more. Okay, I'll talk about that next. Okay. So another way, it is actually now a standard called INT, in-band network telemetry. So what they do is that as the packet go through the switches, you append queue statistics, onto the header. So when the packet reached the host, you just strip off the header, and now you have the statistics of the entire path. And of course, you can look at how to reduce the amount of data collected and stuff like this, but you still add a lot of overhead, right? So of course, the natural thing is that no, I want it to be reactive. Reactive means that only collect when bad things happen, right? But if you're reactive, then, and since you do not know when it happens, right? That means you actually lost this idea of retrospection. That means you always get the data after bad things happen. And also, if you collect it this way, that means that if there's a packet drop, you might not see your packet at all, right? So INT are very useful, but they probably still cannot handle some of these transient fault. They are good for monitoring on the average. So what we have proposed basically says that, you want all 3 of them: visibility, retrospection, and correlation, right? So for visibility, you have to collect on the packet level, but you want to reduce the amount of overhead, so you can do some kind of a compression, right? And for retrospection, I think there's a timing running in the background. Okay, for retrospection, you don't have a lot of choices. If you want the history, that means you have to record continuously, right? You need, because you need to know that you want to know what happens before an event, right? So that means you have to record it. So now the trick is this, right? Most of the time, nothing happens. And if you do continuous recording, how much do you need to keep, right? So what we do is that we actually keep the most recent, let's say, for example, 1 million packets. And then when something bad happens, and then you store it in kind of a circular buffer. And when something bad happens, you freeze the circular buffer. And then all you have is the past 1 million packets. Okay, so means you keep the recent history, and you basically and on the event of a fault detection, you only need to tell the controller or the monitoring agent the packet history before and after, right? Because you have the exact point of where the event happens. And for correlation, we implement some kind of a time synchronization protocol. We have our own actually called the DPDP, published in SORS 19, right? So you put all these things together, we call it synchronized or synchronized network a debugger, right? SyncDB. So okay, so kind of roughly how it works. When you start, you have to synchronize the the entire network based on running DPDP, and then you have a ring buffer that stores the most recent. It's something that you can configure. Now, let's say 1 million packets that you've seen. You only store the headers, right? And then you have the ring buffer will store what you call the P records, right? Which some statistics about the ID in terms of a hash, the time in, time you spend in the queue, and some other programmable statistics, because you can program this, so you can change what you want to monitor, right? Okay. So basically now the network runs, right? So the ring buffer will store the most recent so-called data. So let's say now you detect a fault, right? So what is the fault? Again, it's something that you can program, because you can say, okay, for example, in this case, if my queuing delay exceeds 10 or 20 milliseconds, then I have a congestion. So I should now trigger, okay, and a data collection. So for example, if you triggered, you detect that the queue now has built up here, very high queue delay. You actually now you would basically now send a trigger back to everybody who sends data to you, and everybody who get this high priority monitoring packets will now freeze their collection, right? And and then now they will continue to collect, let's say, for another 1 or 2 milliseconds. So now you have the data for before and you have after. And after that, you will send it back to the so-called the collector, or the guy who does the debugging. So that means now you actually have a way to program the network to collect data only at a certain time, and you have a way to collect all the data. And right now, once we collect the data, we just use a very basic SQL query, and you can say, okay, I have seen a congestion event here, high queuing burst, tells me who are the packets that actually contributes to this microburst, and when did they send a packet. And because you have the ID, you can even trace back potentially to the application. Who are the applications that send packets that contribute to this particular congestion event, right? So I guess a lot of these things might seem obvious to you, but it cannot be done right now, right? This is how you think you want to do debugging, but this is only possible now because we have this platform where we can do all this programming, and we can implement all these functions now in the switch, right? So we actually implemented, and this is all the details. So I said it's programmable. I said you can even program, what trigger you want to collect, how you want to trigger these things, right? So I mentioned, microburst as basically kind of the motivation, to have this platform. But we look at it, right? This is actually useful in general for many other use cases. You have a timing box, either due to applications or due to routing. With this tool, you can do the debugging. Of course, you can have very fine-grained traffic pattern analysis. You can detect loops, or you can detect, transient fault due to a temporary network update. Because if you update the network configuration, it could be that for a very short while, the updates are inconsistent, and that might cause you to have packet loss. And those are things, again, very hard to debug because it happens only for a short while, and it's due to the interaction of many switches. So with this tool, you can actually do all this debugging. So I just mentioned one more use case here, which I thought was interesting, is that when we did it, right, we got a complaint is that very often you know the problem, and then you create the scenario, and then you're going to fix it, right? So you know the answers, of course you can find them. So we actually came out with a case whereby we just let the system run, right, for minutes. And remember that, you know, bad things happen kind of randomly, right? It's a transient fault. So you run it long enough, strange things will happen. So we have a case whereby we have a fan in from H1 to H6, send it to H8, okay? And suddenly we detect a microburst, okay, on S7, the last switch. But it is not due to those guys, the traffic from H1 to H6. It happens because there was another flow from H9, okay, this dark blue line, to H6. That means H8 don't even see this flow at all. But because of this flow, it causes a temporary bursty traffic on S8, which then causes the the burst on S7, right? So basically, our tool can actually now do the debugging. This is the part whereby the traffic from H9 to H6 is sending. So over time, it created some kind of queuing on other switches, and even though it's gone, right, it actually result in a microburst on S7, right? So when we're saying that our tool can actually find bugs that you don't expect, and we have kind of run it ourselves, and we think it's useful. So it's a non-synchronized fan-in. Okay, so this is work. Actually, this is part of the work that was actually sponsored by Facebook, because on network monitoring. Okay, so I'll go on to any quick questions here. I think I have one question here, right? From the chat. Okay, so I think the questions from one of the question was that can you detect? Is it okay? You can detect microbursts, right? With the current switches, but you can't do the debugging. You cannot explain, who contribute. What are the you can explain it. You know that because microburst just means you have a packet loss, right? And the system now allows you to know that there was a burst of traffic causes packet drop, but you cannot find out more than that, right? Because it's a very aggregate information. Roland said, how do you fix microburst? I don't think you can really fix it per se. It's one of those things that
no, I mean you are debugging, right? But
yes,
the end result of debugging isn't it to fix something?
No, yeah, kind of. If you understand the cause, hopefully you can reduce it from happening. That's the idea. You can hopefully reduce the likelihood of it happening. You can't really fix it. I don't think you can fix it.
For example, it only happens once, right? Like, yeah, and you already saw it. It's too late already, right?
Yeah, correct. So but
and then the next time is due to a different reason, and so on and so on and so on.
Yes. But hopefully, if you fix the previous one on come back, it's one of those things, right? You just have to keep fixing. But if you don't fix any of them, the number will just keep growing.
I see, but how do you fix it? I mean, you have to change some policy or something.
Yeah, that's something that we always say in the work. It's like debugging, right? I give you a GDB debugger, okay, so you can debug it now. How you fix the bug? The programmer how to do it. This tool only lets you see it. It's not
right. But in the normal situation, right? Like the guy doing the debugging is also the guy creating the problem.
Yeah. But now I have a tool.
But in this setup, right? Like you're debugging, but it doesn't mean that you control over the fixing, right?
No, say we will give the tool to the people who manage the network and run the application. So
right. So you manage network, but if you're not running the application, you can't do much, right?
Yeah, but now I can report. I can, because sometimes they want to do root cause. They want to know who causes it. They just want to attribute the cause. That's the first step. This tool, you can do root cause. You can explain who contributed to it. How to fix it? It depends on many factors, right? You can move this guy to another cloud that's more isolated or something, right? So fixing it is really beyond this part of work. Yeah. Okay, so let's go over to the next one, right? So next one, okay, is about here for monitoring, we just do thresholding, right? Because this is probably the simplest way of monitoring. In general, when you do monitoring, and you want to do it in a data plane, right? Because you do it on the kind of the net flow level, you are doing a lot of sampling and aggregation. So what you want to do on the network level is that, there's people want to do it for load balancing purposes. They want to monitor for faults, right? They want to characterize the traffic so that they can understand it. There are a lot of stuff you want to do. So there are a lot of things that people want to know about the traffic, and you want to do it in a data plane because you have the best so-called visibility, right? So the idea is that you really want a data structure, a way of doing it that really fits, how the hardware looks like. So you want to be simple because you know about the hardware, and you want to be as accurate as possible, right? That's the whole idea. So since you run it in the data plane, usually most of them are based on some kind of a sketch, right? So a sketch is, is I guess, I'll try to be quick here. It's basically a probabilistic data structure that can run in constant memory access, is very memory efficient, right? So the classic one is called the count min sketch. So imagine, you want to count the number of packets for this particular flow. So what you do is that you hash it to, let's say, 3 different entries. So there are many flows here. I mean, there are many flows here, but when you do the counting, you map it to 3 different ones, right? So of course, the risk is that you can have multiple flows matching to the same entry. So the way you do is that you say, okay, I have 3 entries. Hopefully, there will be collision, but they're not so bad, right? So when I want to know the number of flows, I look at the minimum of all 3 values. You're hoping that among these 3 entries, one of them is only used by you. If all the entries are used by everybody, then you overcount, right? That means you actually your memory is not enough, right? So count min is a very popular structure they use in the even the hardware or your software, because it's very simple and it's quite efficient, right? So anyway, so count min is fine, but it has certain problem because first, right, the traffic is highly skewed. So if you use the same size counter for everybody, then you realize that in order to not to have overflow, you need a sufficiently large counter. That means you tend to use a bigger value for everybody. But that means that you are okay with the large flows. Or for the small flows, you're using a memory that is very large, but they're only like very small number of packets anyway. So you're wasting most of the memory, right? So it's underutilized. So of course there are a lot of proposals to solve it. So one of the kind of the more recent proposal is something called Elastic Sketch, SIGCOMM 2018. So it says that kind of very again logical. You separate the flows into 2 kinds, the big ones and the small ones, right? So you first have a data structure, a much smaller one, to capture the elephant flows. So if it doesn't fit into the elephant flow, you count that using a smaller entry, right? It works quite well. It makes a lot of sense. There's only one, not only one issue. One of the issues is that it works well, but this part, right, requires some kind of a periodic update and requires some kind of a sorting. You need to find the guy, right, the smallest elephant to evict. And this means that you actually can't do it in hardware. So it works well in software, and hardware you actually cannot implement the way you want to. So you have some approximation, which basically destroys the accuracy, right? So it's a structure that would work, but cannot be exactly implemented on the hardware, right? So again, there are many others, other similar proposals. So just the question now is that how can we design one something like this counting, and yet a small amendable to be implemented on a pipeline hardware like what we have now. So okay, you look at how count min does, right? Count min will have a sufficiently big a memory for the large flows, and then you just sort them right into one of the entry, right? And the entry is quite big. So the alternative way is that you remember that you have this highly skilled, you have a very large number of small flows, and and then you have gradually more smaller and smaller elephant flows, right? So you think of it, your count min is only two levels. So think of it, it's kind of the natural, the logical way to do it is that you build a tree. So on the leaf level, you can have a very small counter, and you can have a lot of them. And then the next level, you have a slightly bigger counter, and then the higher level, you have an even bigger counter. So the complexity now is really designing the data structure to do the update so that you can still count, right? So the packet comes in. If there's a lot of small flows, I'll basically populate this part quite well. I have a lot of them. And since there are less and less small flows, so I will just have less entries here, but bigger entries, right? So this is something that we call it feed-forward count min sketch. And there are some nice features about this. Besides the fact that it is highly so-called suitable for skilled traffic, which is true for most of the network traffic, it also is very suitable for so-called what we have the pipeline. We have a pipeline, right? So the pipeline is actually how the tree looks like. So each of the level goes into one stage. So now this actually is very kind of fit nicely into how the hardware looks like. You have stages, at each stage you have a different set of counters. So in fact, if you implement FCM in software, it's actually quite slow because it's harder to parallelize. But in hardware, it's very fast, right? And it doesn't take that many stages. So it is almost it's more complex than a count min, but it's still simple enough to be implemented in hardware, right? So I guess I'll skip the rest. But what we found we are quite happy is that we published it last year. So this is the evaluation done by somebody else. So another group from CMU, actually they were talking about how you can take any of this sketch proposal and optimize it to run the hardware. So they are the one who designed something called a Unimon. So they actually, via our code is is open source. They took our code FCM and they compare with theirs, right? You can see that actually, even though we actually did very well for up to like 5 million flows, right? So it's kind of towards a validation by other people, not by us. They show that our code runs and runs quite well. So of course we don't scale for very large flow, but this is really a matter of the memory size. If you need to count like 100 million flows, you probably need more memory, because the trade-off is this: for smaller flows, they actually have reasonably low accuracy, right? So I guess a trade-off. Do you want to give more resources to achieve higher accuracy, right? Or you just want to say that I'm happy with a few percent, right? So okay, so I guess I would like to. Should I end quickly, because I have one more quick topic to cover for this fronthaul. I already hit 1 hour. I know I'm very slow. Can I get some?
Since we started 7 minutes late, so probably if you think it can be done in the next 10 minutes.
Okay, sure. I will try to be quick. Okay, so this third part is about how do we use something like this to help you to make 5G better, right? So of course I skip this part. You all agree that 5G is emerging, important. Okay, the key thing about 5G, right, that really of interest to us is that 5G stresses the need to have differentiated services, right? What do you mean by that? Is that you have at least three extremes. One is so-called the high throughput. We all know, right? High throughput, you can do VR, AR. Another one is that you wanted to do remote control, like autonomous vehicles. So you have a high reliability and low latency. And the third one is that you want to support IoT. You want to support very, very large number of low power devices. So these three types of traffic applications have different needs. That means you cannot, like the internet, best service, everybody's the same. So you need to do so-called slicing. You need to have the capability to differentiate the traffic inside the network, right? So that's why the traditional design is that you have your antenna, right, your base station, and then you have a single wire. You go to the host, right? It could be an ASIC. You do all the radio processing. So in the 2G is optimized for voice, and the 3G and 4G optimized for data. But it's only one service type. Okay. So the fronthaul is basically the guy that connects the front end, the radio front end, to the part here that does so-called the radio processing, right? So and another trend, okay, and there's another trend in so-called the 5G world is that they are trying to, two trends. One is that they try to make the front end, the radio, simpler. Why? Because they believe that to have good coverage and so-called better spectrum reuse, I want small cells. And I want many small cells. And since I want many of them, I want them to be cheap. So they want to move more work of the processing to the backend, right? So simpler front end, more complex a backend, right? And second thing is that the backend, old days they tend to use ASICs. Now they say that I have all these clouds, around the world. If I can, I prefer not to build my own ASIC. I would like to run my radio processing on more traditional software. I can run it on the cloud. I call it cloud RAN, right? So the two trend, move the processing to the cloud, and the cloud you want it to be generic a processor, so they can use all this available stuff. So from here, you finish all the wireless stuff, you send to the core. So here onwards, you have your normal internet packet, right? Okay, so this is how things are. We have voice or data only, but with 5G, you have different so-called different service type, right? So you have all this, you know, different service types, different colors, and they can attach to the same front end, right? That means that now each of these host processing component unit also needs to process different categories now. But then you have high throughput, you have low latency. So it means that now you need to build these things in a specific way, right, to make everybody happy. I said, well, this sounds very expensive. So why don't I have different processing elements that are more suitable for different kind of services, right? So it doesn't make sense to have a single hardware type to process them. I want the flexibility to process them. And of course, once you have this, right, you look at this, right, of course, you don't want to do so-called do peak rate. You don't want to, build these things to support the maximum of all the base stations, because most of the time, only a few of the base stations are busy. The rest are not doing much work, right? This is the standard, statistical multiplexing. So you actually want, finally, right? See, the traditional is point to point. This is how things are built for all these years. You can say, why? Because there's no need to go to multi-point to multi-point. This is the point-to-point is a simpler way to build. But since you want to have different services, you want to have different hardware types, so it makes sense that you have a multi-point to multi-point connections. Any user of any type from any base station could be processed on any of this hosts. That means you need a multi-point to multi-point connections here, which doesn't exist before. Right? This is something that is new. You might say it's obvious, but it's not there, right? It's something that's new. Right, so on one hand, processing can be done on any of the hardware, and the users can be anywhere. And in order to match any user to any processing element, I need multi-hop routing, right? Multi-point to multi-point routing, right? So okay, so how do you do this, right? So how do you do this? So the high-level story first, okay. Because of the way the wireless channels are designed, you do very little processing here. So when you are done with whatever you do, right, whatever come out here is very low level. We call it the IQ pair. It's just a lot of bits. You actually don't even have the ID of the user. All right, so this is very hard, and also you have very high throughput. Okay, the front haul throughput can be up to 300 gig per base station. A very high throughput, the max, right? So that means that you cannot even identify the user when they come out. All right, so the way to solve it, okay, is that actually there's a scheduler that decides which user is allowed to send at what time. So you can actually use the information from the scheduler to say that, okay, I can coordinate, at certain frames. So you need some kind of timing information. Certain frames that come at a certain time, I will route it to a certain host, right? So using some timing information, I can do the routing because the sequence is known, right? So this seems to at least address part of it in terms of identification, right? Okay, now the harder part is that, okay, let's say if this is done, but I cannot actually update. That means I'm doing the routing now on this part here now. But the issue is this, that you cannot pre-program this, like how we do normal routing, because the number of users per base station can be very high, right? Because a user in this case just means like your mobile phone, right? Like all of us are, have a phone now, but our phone actually is somewhat attached to the base station, but we're not doing anything, right? So you can't have an ID of all of you even in the router. All right, your ID should only have a meaning if you are sending packets. So you cannot so-called pre-program all the IDs into the routers. There's a lot of them. Plus, who is allowed to send, right, changes every milliseconds. The scheduler runs on a time scale of every milliseconds, and every milliseconds up to 10 new users can send. Let me think of it. You have a very high frequency routing update here, right? So the updates here is very high, on the orders of like 100,000s or millions per second. This is not how the traditional routing work. Your BGP routing, your OSP routing don't run this kind of time scale. The routing is actually much slower. Here is on the orders of milliseconds, right? And it's over all the base stations and all the users. So clearly, since I'm kind of leading you there, right? The way to do it will be that you do the routing update in the data plane, right? That means that you are given the scheduler, you actually send the schedule and in a form of a routing update to the switch. And then the switch will send the schedule to the base station, right? And in the process, the switch upstate its routing table in the data plane. All right, everything is done, in the data plane, and when the packet comes back, the routing entry is already updated and ready so that it could be sent back to the right host. Okay, let's kind of okay, let's see how it works, right? Okay, so roughly now this is how we add. So we have a network scheduler, and the way the system works is that you actually decide on the schedule about 4 milliseconds in advance, right? And this is done for every base station. Okay, so we will think of it, we will kind of logically think of the routing table in the switch as a ring buffer. So now the schedule will be sent to the router. Okay, he will basically say, okay, I update my routing table here, all right, and I have only one user, and he uses what we call 2 resource block. And then in the next time schedule, all right, I have now 3 different users. Each one of them consumes 1 resource block. So this schedule will then be forwarded to the base station, right? To the radio to actually schedule the real user, and it comes back. Right. So now let's say I schedule four of them, right? So now when you start getting packets from the base station, you will get 2 packets, right? And so now I'll advance my pointer to the next one. So it means I tightly synchronize the schedule and the transmission, and I make sure that my routing table contains the right set of routing entries. So this may look a bit fragile to you, right? But I won't go into the design, but we make sure that we can handle packet loss, a small amount of packet loss, and we can handle packet rerouting. There's sufficient redundancy built in that you can do all these things. Okay, so we have implemented it. We can run it. So the key thing, this is a very different way of how to think about how the 5G front haul can be built. I think we are one of the first group that kind of show a way whereby you can use a programmable switch to kind of to support some of these new features that people want in the front haul. Okay, so just to show you that it works, is that basically one of the concerns is always, if I send a schedule packet to the router, can I update the schedule, the routing fast enough before the packets return, right? Because I update, and then I forward the schedule packet to the base station, and then he sends the packet out, right? So can I make sure that I update and it's completed before the packet comes back? So this is basically the update, right? If I update 4 entries or 10 entries, that's how long it takes, about 2 microseconds. So we assume the worst case, as in the moment I send out this schedule, the packets return immediately, right? Normally this is not the case. You will return after a few milliseconds. But even if you return immediately, the schedule will still be populated correctly in the routing table before the packet arrives. So this is the 4 entries. The solid line is for the 10, right? 10 entries. So we have more than enough time. And another one is that if I were to send a schedule from the scheduler to the switch, how long does it take, okay, before I can update the entries? To this point, it's about 6 milliseconds. That means if you add up the entire thing, is we have enough time to populate the routing table and get ready for basically the packet to come back. So we kind of run a more realistic, we actually implement it on the switch. We have some kind of a trace to send traffic, and then we send it to the 4 hosts. So we have 5 users of different types sending to 4 hosts. I think we run for about 2 minutes, sending about 1.3 million packets. And basically what we want to show is that every packet get routed to the right host, and that in the meantime, during these 2 minutes, we even purposely, throw in some issues with packet loss and stuff like this. So overall, basically it works. And once you can do this kind of slicing, right, we kind of demonstrate that we can also do so-called prioritization. We can actually implement a specific, scheduling algorithm to so that I'm aware of the deadline, because all these 5G stuff are very deadline driven. All processing must be completed within, like 4 milliseconds or 2.5 milliseconds. So you can actually schedule the packet that is more have a shorter deadline first, right? So you can do all these things. Okay, so I look back. I think so. Roland said is the round multi-point to multi-point. Yes, multi-point to multi is a
Yeah, I
kind
think
of
you
routing.
addressed it already.
Yeah, correct. Yeah, okay, sure. All right.
But,
so
but is it a problem with the 5G protocol?
it basically is it kind of, it's not a problem. It's basically what 5G wants.
No, I mean that this multi-point thing could be sort of embedded in the protocol itself, right?
It's actually a requirement in the so-called in the newer standard, which is not there before because they don't need it. So now they actually want it.
So they changed it actually.
Yeah, or they enhance, because they said that if they want to do this kind of flexible load balancing, they need multi-point to multi-point, which they don't need previously. So this is a new requirement. Yeah, and it's not easy to support because of the high frequency update that they need to support. Okay, so this is my last slide. I hope I'm not too low. Okay, first, I guess the emergence of such capability, open up many new interesting possibility that you can, think about, how you can build new systems. I think one of these things that also kind of clear to people who work on this is that now, right, you can potentially have a very, very short and high resolution feedback loop. Now, previously, let's say for now, people, like TCP, right? You run TCP, you very often you have no clue what's going on in the network. You just react according to some estimate. So here you actually you can have very good idea of what's going on in the network, and it comes back very fast because everything is done in a data plane. So you have very good information and you have very short control cycle. So that could potentially improve a lot of this algorithm. Right, so I guess people are looking at basically how you can design new way of doing things. So and I think I didn't add in so-called the NIC card. So the NIC card means the network interface card will also play a very big role because I only talk about all the switches. But the end-to-end is basically you have a real-time CPU, you have a very capable programmable network interface card, and you work with now you work with a programmable network. So now everything is programmable and everything has very short and high resolution, information. So you can really do a very good job in controlling the end-to-end behavior. Okay, this is my last slide. Thank you. Any other questions?
Thank you. I guess we can have some quick questions and perhaps.
Sure.
Yeah.
Happy to.
Roland?
Yeah. Yes, Roland.
Yeah.
So I guess it's really a trade-off between processing speed versus power, right? I mean, how much computational power you want to have, and the network always trying to be faster, right?
I mean, that's what
so is that going to be like killing yourself kind of thing?
I would say the network it tend to be faster because it does less work, and I always think also if you can do it in the network, you also cut down on the latency.
True, but then suppose you want to have the terabit internet or whatever, then do you have enough time to do the things you want?
Yeah, but you're correct. It's already true now. I mean, right now the even the oldest version of Tofino 1, the backbone is 3.2 terabit, right? So next one is 6.4, and next one is 12.8. The core is switching fabric is already like 12 to 20 terabits. Not the links. The links will be maybe 400 gig, I think, at some point of time. But I guess I think the key thing is how to be smart about knowing what you want to run in the network and what you want to run in the endpoint. Because previously you don't run anything in the network. You just avoid it, right? Now the network have some capability to help you. So what is the right thing to do to move to the network? I think this is the kind of where people are thinking, and some people are getting too aggressive. They want to do like, AI, machine learning in the switch. People are trying, but I guess, it doesn't work very well right now.
Maybe that's not really doing the right thing, but probably using the wrong thing for the.
Yeah, combination of finding the right functions to put. Plus, I think again the network will be more capable. I know for Tofino 3, they are looking at what are the hardware features they can provide that can be helpful. That's where they are going. So I think more
the hardware probably has to be fixed, right? It cannot be FPGA. Like FPGA may not be fast enough for you.
Yeah, correct. It's still an ASIC, but the ASIC you can download so-called your P4 code, your microcode on it in runtime. So it's of course an ASIC, but you have some levels of
I mean, there are people who sell network gear with all kinds of FPGA stuff inside, right?
Oh
So
yeah,
is
this
that
is
what
not
they're doing
FPGA.
also?
No, FPGA tends to be more on the NIC card. Though these are more common. Yeah, on the NIC card, there are more so-called FPGA based NIC card that, because for FPGA they feel that they want even more capability, that the switch, because the switch fundamentally is still a switch. You don't want to slow it down, right? There's a hard timing thing. So for NIC card, because it's only a single host, so they are selling basically FPGA NICs. So now I think you might have a P4 compatible FPGA, because I mean you want a language that so-called common across both platforms. So I think I'm also looking at so-called coming the P4 compatible, so I can write one code, right? They will run on the switch and run on the NIC card. That will be more convenient. Because I haven't really done it myself, but the feedback I got from the students is that you run very long all these things on the FPGA is rather painful. It takes a long time to do the compilation is very, very long. P4 is much faster. It's just basically still not as fast as the C compiler, but it's fast enough. It's basically you compile and you run it. Yeah.
Right. But then your ASIC is fixed, so
correct. Yeah, it's a trade-off between your flexibility, capability versus
Then I had a question about the previous thing where you said you can just loop back the packet.
Yes.
Wouldn't this cause a problem with packet drops or something like this?
No. Okay. Basically, if you loop too much, right, you create queuing inside the switch.
Yeah. That's so that will cause you a problem, right?
Correct. But like in this case, right, we actually do a loop back, because remember I said that every time you go through, because I need to update. There's 10 user per millisecond. So when the packet hash actually need to update the entry 10 times. And if I do it one shot, right, I mean I use up 10 stages. The switch only have like 12 stages. If I take up 10 stages, I have no more space left to do any other stuff. So we only want to use less. So let's say if I only update 4 entries per loop, right? So I'll loop back my packet now to complete the other 6. So I loop back 3 times, 4, 4, 2. So in this case, I have to do a loop back because I just don't want to waste all my stages on 10 updates. So I use the loop back to basically speed up the processing. So loop backs are useful some of these things. We also have some other work that also use a loop back. Even for the one on SyncDB, you can also do a loop back because you want to store the last 1 million headers, right? You can also do it through a loop back. That means you will loop back, if it comes back, you don't need it, you just throw it away. So you use the loop back as an extra buffer. Right. So it's a loop back, but people use it for different purposes. As an extra buffer, as a way to spread out my processing over.
It's a bit like a TDM slot.
It's like kind of a spare capacity that you can use in some form. Yeah.
I mean, like an optical ring, right? You use the ring itself as a memory, right?
Kind of,
because you use it as a delay loop, right?
Yes, exactly. Yeah, correct. Kind of similar. Yes, yeah.
So Manchun, I have a quick question, but actually it's also related to the question that has been pasted in the chat by Moi. Maybe he can go first. He already pasted his question, and then I'll just follow up. My question is related to his.
Okay, so let me read Moi's question, right? So programmable switches require hardware upgrade to the existing structure. Okay, I get this asked quite often. Okay, for you share the current status, right? The big players. So when you talk to the vendors, when I talk to Facebook, these people, right? They are very intrigued by the capability, but they are not ready to change because they have such an immense so-called installation of their white box switches. So in the short term, I don't think they would do it, right? But then the question is that, I mean, for us, we have a longer term horizon. So things that if their switches will need upgrade in the next 3 to 5 years, when they need to upgrade, right? Will they go the route of programmable switches, which I think is likely, because even they use programmable switches, right? They might not use so-called exactly the open source. So because it is at the end a very flexible and a very convenient capability. So I was told Cisco, Juniper, all these big guys, they may be using internally programmable switch to do their own development. So they will use it because this will make it easier to do the development. But when they sell to you, they will not give you the APIs, right? So you can think of it. You can either work for think of it as a white box, like Facebook and maybe Google, Microsoft. They would go the white boxes. Then they might, as they upgrade, they might go to programmable switches, or the Cisco folks will use it internally. So I somehow see that over a medium-term horizon, something like this will be more popular. The only thing is that would it be as open source as in everybody can go and program, or they keep it more as an internal development environment? I see it happening actually. It will at least be used internally. It just might not, because it messes up the business model, right? Make it everything open, then how is Cisco going to make money from the vendors from doing the upgrade, right? It's very hard for them from the business model part. But I don't see why Cisco wouldn't use this for the internal development. It's really useful. And the rumors I heard is that they are looking at it, right? So again, it might not be P4, it might not be pizza, but it'll be some version of it, I think, yeah. And sometimes why not, right? I mean, they can always use it and use it internally because it's already there, it's already available. The only fear is that Intel is the big guy now. Are they worried about depending only on Intel, or they're looking for more vendors? So this is something that I'm not sure. So yeah, short term, I don't think you will see it. Medium term, I'm somehow quite positive it will happen in some form,
I guess.
Okay, so in fact, I mentioned, right? So this P4 runtime is actually led by Google. So I was told that the way Google look at it is that they buy switches from the white box switches from different vendors that is open, right? Google doesn't want to be tied to a particular vendor. So they said to this vendor, okay, I want to manage my switch. Okay, I don't care how you built it, but when you sell to me, describe to me the behavior of a switch using P4. Right? You build the way one, but you export to me a P4 like interface. So for them, they will just say, okay, your switches can be described by P4, right? Then I will then use the P4 runtime. I will generate my own set of APIs. So this is another way to use it. They just have to comply to the thing. So Google don't want to make it, but say you have to make it according to the spec. And the spec is a P4 like behavior, which I think also make a lot of sense for them. Yeah. So I guess for the software engineering folks, this should be something very interesting, right? Because you specified the behavior. Then you can do all basically verification. It's just really, I don't go into that, but there are a lot of papers, even in SIGCOMM, that talks about how to make sure that the behavior is, compliant and everything. So there's a lot of effort even in the SIGCOMM community that looks at behavior verification. Okay, so
we have time for one last question from Abik.
Yeah, I think I will keep it very brief. We are already
sure.
we can follow up offline. So you already addressed part of my question. I had kind of two quick clarifications. You already addressed one of them related to the behavior. The other one would be like a very long-term view. Like, for example, in the US now, there is a lot of funding, right, on this software-defined hardware. So as that becomes more prominent, what do you see? This programmable switches, the current work on P4 and programmable switches, would there be further impact on that? Because the hardware also you can now configure in the software. So what impact do you see that kind of a funding program having on the future of programmable switches? The other part is already addressed.
Okay, okay, because it's all, I don't know what the future will hold, but my guess is that, right now, this is more still specific to the networking community. Like, for example, I know there was this recent grant this for NSF, like, I don't know, like 30 million grant called Fronthaul, right? So they are basically looking at programmable switches in the context of so-called private 5G network. That means, you build your own 5G that only runs within a factory or the pod or the, private, right? So to me, that's very interesting because again, it's not about the networking, but it's a networking goal with a specific domain. Right? So I see that maybe the trend is that, people will look at this and say, what are the good ways? It's like the internet, right? I mean, if you focus only on the networking part, you can only go so far. As the interest comes with how people can use it, right? How can use it to extend the capability of the application. So again, 5G is still very much communication, so it makes a lot of sense. But maybe there will be other kind of domain applications that they believe that a programmable network would benefit. So you might then go hand in hand with some other domains. I think you won't be networking alone. You'll be. So I think the next, at least I won't say long term, the medium term will be programmable switches plus some other domains.
Yeah, thanks. Yeah, I think we should take it offline. Yeah.
Sure. Yeah.
Okay, so I guess that's a good time to end today's colloquium. Thanks a lot for a wonderful talk and
thank you.
answering all the questions. We'll be resuming our series in the new year on January 20th. You'll get an email before that.
All right. Okay. Thanks guys. Thanks for attending and asking questions. Okay. Thank you. Bye bye.
Thank you.